Hi, I'm Phil Webb, Principal Consultant with Select Business Solutions. When you write code, how do you know that it works? That it does what it should do? Do you manually check it, step through it in the debugger and verify that it's working? Or do you check the output of the program, say the web page or the database, and work out whether that's correct? How much time does this manual testing take you? How good are you at testing your own code? How confident are you that you've covered everything and that it all works? Later, after you've checked it, how do you know that it still works? How do you know that the feature you added yesterday didn't break the code that was working last month? Traditionally, programmers have designed their code, implemented it, and then tested it. Each of these phases were quite long. Sometimes each phase took months. Testing especially was very long and often ran over its scheduled time, which caused the whole project to be late. Sometimes as many bugs were introduced each day as were fixed, and the project could never get finished. Testing was mostly manual. Manual testing was not very thorough or repeatable, so a lot of products were and still are pretty buggy. Regression bugs were very, very common. A regression bug is when something used to work and then stops working because of some new feature or bug fix. Because of the threat of regressions, manual testing takes a very long time. You have to retest the whole product after every change, not just the part of the product that has been changed. So as the product grows bigger, the amount of time needed to test it grows. The other reason testing takes so long is because most of the time labelled as testing isn't actually used to test. It's used to fix the bugs that were found during testing. Yet another problem was that as the code base grew bigger, it also grew more and more fragile. So the chance of putting in a bug when you were doing some new code increased as the code base grew. So there was a high cost of change when working with large code bases especially. The bigger the code base, the more features that had been implemented, the longer it would take to add to the code a new feature that wasn't predicted. The response to this high cost of change was trying to nail more and more things down in the design phase so that there would be less change later on. However, it rarely worked. Things could never be all decided in the design phase, and even if they had been all decided for version 1, what about version 2 and version 5 and 10? Code spends most of its life in maintenance phase, that is, being worked on after it's been released. But it took a while for people to work out that trying to stop change was the wrong thing. Instead, we needed a software engineering discipline which embraced change and which lowered the cost of change to software over time. These smart guys were Kent Beck, Ron Jeffries, and the other founders of Extreme Programming. Out of this desire to lower the cost of change, to make software more malleable and easier to change over time, came test-driven design, sometimes also called test-first design. In this philosophy, instead of having 3 distinct phases, design, implement and test, we turn it around and do test, design, implement. And each of these phases are much shorter than the original phases. Instead of a phase taking several months, they take more like several minutes. We work in small steps, which are all so simple that we can't get them wrong. So test and design are one phase. We design the system by writing tests which will use the system. This helps us to design a system which is easy to use and easy to test. A byproduct of this design activity is automated unit tests, which can be easily run to prove that the system still works. This means that we can easily and quickly regression test the whole code base and verify that we haven't broken anything that used to work. Not only that, but if we do break something, we can fix it straight away, within a few minutes of breaking it. Which is, of course, the cheapest time to fix the bug, because the longer a bug has been in the system, the harder it is to fix. A long-standing bug is hard to fix for two reasons. Firstly, new code may be relying on the buggy behaviour, so it's now impossible to remove without breaking something else. And secondly, it's harder to remember why you wrote the buggy code and what you, or indeed someone else, was trying to achieve when you wrote it. So writing automated tests and running them every time you change the code base allows you to verify whether your new code has any unexpected side effects and to fix any bugs which were introduced immediately. This is much quicker than having a long testing phase at the end of development. It also makes you braver. You don't need to be scared to change the existing code in case you break something, because you know if you do break something, you'll find out straight away and be able to either fix the bug or simply revert the code you added. So test-driven development is the practice of writing an automated unit test to test your code before you write your code. But how does it work? How do you do test-driven development? Start by thinking about what you want to write. Then write a test that would prove that you have written what you intended to write. Then implement the code so that the test passes. Then run all of your unit tests and check that they all still pass. Then you refactor the new code you wrote to make it easier to maintain. Try to name everything as well as you possibly can and to remove all duplication. Then run all of your unit tests again to check that they still all pass. And then you check your code into source control. Smile. You're one small step closer to achieving your goal. This whole cycle is very quick. It should take no more than an hour to complete all of these steps. These tests are unit tests, not system tests. They don't test that the whole system works. They only test that the function you just wrote does what you wanted it to. However, if you've tested every function you wrote, you can then feel pretty confident about the whole system working. Of course, you still do need to test the whole system like you used to. However, now you should not find so many bugs. As much of this testing as possible should also be automated. That's then called automated acceptance testing. In the following sessions, I'll be showing you lots of examples of how to do test-driven development. Test-driven development can be done in almost any language, and there are many different tools you could use. But for the sake of simplicity, we'll do the whole demo in C#. Therefore, we'll be using Visual Studio and some of the related Microsoft tools. But all of the principles can be applied to any language and IDE, for example, Java or Ruby, Eclipse or IDEA. There are XUnit frameworks for most languages, JUnit for Java, NUnit for C#, CPPUnit for C++. There are frameworks for JavaScript, PHP and Python. Check out the extensive list of software links on xprogramming.com/software to find the XUnit framework for the language you work in. Most of these tools are open source and free to use. In these demos, we'll be using the unit testing framework that comes built in with Visual Studio to save you from downloading and installing more software. But on a real project, I'd probably use the open source project NUnit. As well as an IDE and an XUnit framework, you will also want a mocking framework, refactoring plugin, continuous integration software, and a dependency injection framework. Again, there are many choices for each of these. For instance, you might use Rhino Mocks for mocking, ReSharper for refactoring, Team City for continuous integration, and Unity for dependency injection. In the following sessions, we'll work through some examples of how to write code using test-driven development. I'll also show you how test-driven development is about design as well as about testing. We'll cover basic tests using red, green, refactor, and then move on to more complicated tests using mocking frameworks and dependency injection. We'll also discuss continuous integration, testing databases and web pages, and behavior-driven development.